The Great Pyramid of Giza stands as a testament to impossible precision, its stones locked together without a single modern tool. How did ancient builders achieve such perfection? This journey uncovers the evolution of early stone cutting techniques, revealing how simple innovations led to the world's most monumental architecture. You will learn the exact methods that allowed civilizations to shape mountains into monuments, from the first hammerstones to the secret of splitting granite with wood and water. We will explore how a dangling piece of string brought unprecedented accuracy to construction, and what mysterious process allowed workers to move stones weighing hundreds of tons. By the end, you will understand the foundational engineering that connects our modern world to these ancient marvels. What forgotten skill from the past do you believe we have lost today? That first sharp crack of stone against stone echoed with more than just sound. It held the resonance of a future being shaped. In that seemingly simple act of striking one rock with another, early humans unlocked a fundamental truth. Certain types of stone, like flint and obsidian, possessed a hidden grain. A skilled hand could use a harder hammerstone to strategically chip away at a softer core, flaking off pieces to reveal a sharp edge, a pointed tip, or a crude hand axe. This was the hammerstone technique, the absolute foundation of all stonework. It was less about brute force and more about understanding the material itself, about finding the points of weakness and applying precise, calculated percussion. The goal was a functional tool for survival, a knife for butchering, a scraper for preparing hides. Yet the underlying principle was monumental. They were learning to converse with stone, to ask it a question and receive a deliberate answer. This fundamental dialogue between human intention and raw material would eventually scale up from handheld tools to blocks large enough to build civilizations. So how did this elementary skill evolve from crafting a hand axe to quarrying a perfect block for a pyramid? The journey required a leap in both ambition and technique. That leap in ambition began not with a hammer, but with a gentle, insistent push. A master craftsperson would hold a core of flint steady, placing the tip of an antler or a piece of hard wood against its edge. Then, with a controlled, rolling pressure from the palm, they would push, not strike. A long, thin flake would peel away from the core, its edges so sharp they could rival modern surgical steel. This was pressure flaking, the next great conversation with stone. It moved beyond the brute percussion of the hammerstone into a realm of delicate negotiation. Every application of pressure was a decision, a precise removal of material to coax a specific form from the stone. A hand axe was one thing, but through this method, they could create specialized tools, barbed arrowheads, finely serrated sickle blades, and chisels with perfectly straight edges. The mindset required was transformative. It demanded foresight, patience, and an intimate understanding of the material's hidden structure. This was no longer just breaking rock, it was sculpting it. Can you see how this meticulous, deliberate approach would become the mental blueprint for the architects of monuments? The same patience needed to shape a single arrowhead would one day be applied to dressing a 10-ton block of limestone, ensuring its sides were perfectly flat and its corners true. This refinement in small-scale toolmaking was, in essence, the training ground for the grand-scale ambition that was coming. The tools themselves, these razor-sharp flint chisels and gouges, became the very instruments that would allow workers to precisely quarry and shape the massive stones for pyramids and temples. The journey from a palm-sized blade to a mountain of carved granite was now incredibly within reach. But freeing a single block from the earth was only the beginning of the challenge. Once a massive stone was isolated, it had to be moved, and the early methods for this were as ingenious as the quarrying itself. Workers would likely slide the heavy blocks onto wooden sledges. Then, to overcome the immense friction, they may have employed a simple yet brilliant trick, pouring water onto the path ahead of the sledge. The water would mix with the desert sand, creating a slick, muddy surface that dramatically reduced the pulling force required. This was not about raw power, but about understanding physics on a fundamental level. It was a practical application of reducing friction, a concept we still rely on today. Think of a heavy piece of furniture in your home. How much easier it is to shift once you slide a cloth or a mat underneath it. They were doing the same thing, just on a colossal scale. This innovation transformed an impossible task into a manageable, rhythmic process. Teams of workers could then haul these incredible weights across great distances, a slow but steady march of progress. How did these early logistical feats pave the way for the even greater challenges of lifting and precise placement that would define the iconic skyline of ancient Egypt? A dangling piece of string and a simple weight, that was the key to transforming a pile of perfectly cut stones into an enduring monument. This was the Plumbob, a tool of such elegant simplicity that its principle remains unchanged to this day. A craftsman would hold the string, allowing the weight to pull it taut, creating a flawless vertical reference line dictated by the unerring force of gravity. Against this line, they could check the alignment of every stone they set, ensuring each wall rose perfectly straight and true. Alongside it, early builders used water itself as a guide. They carved shallow channels in the stone foundations and filled them with water. Because water always finds its own level, the surface of the water in these troughs provided a perfect horizontal plane across vast distances. With these two tools, the Plumbob for vertical truth and the water level for flatness, guesswork was eliminated. For the first time, builders possessed absolute confidence that the colossal blocks they were lifting would interlock with the ones beside and below them. This was no longer just stacking rock, it was assembling a giant, precise puzzle. Can you picture the shift in mindset? The assurance that came from knowing a wall would not lean, that a corner would meet perfectly, that the entire structure would stand for millennia. This simple confidence, born from a weighted string and a trough of water, is what empowered architects to dream on a truly colossal scale. With every block aligned to perfection, the final, most physically daunting challenge remained: how to lift these multi-ton stones high into the air to build upward. The creak of wooden logs under unimaginable weight signaled another profound leap forward. Teams of workers, armed with long wooden levers, could now pivot a massive stone block just enough to slide a series of tree trunks underneath it. This simple act of prying transformed an immovable object into a portable one. The principle was leverage, a fundamental force multiplier that allowed a small group to control a weight far beyond their collective strength. Once the block was perched on this bed of logs, the real journey could begin. These logs became rollers, a primitive but brilliantly effective bearing system that reduced friction to a manageable level. As teams pulled on heavy ropes, the stone would inch forward, the rollers spinning out from the back to be carried to the front in a continuous, labor-intensive cycle. This was not just about muscle, it was about physics and logistics. The rollers distributed the immense load, preventing the stone from sinking into soft ground and making transport across surprisingly uneven terrain possible. But moving a single block this way required the coordinated effort of hundreds of individuals, all pulling in unison, guided by shouted commands and rhythmic chants. Can you envision the social innovation required to manage such an operation? This scale of labor demanded unprecedented levels of organization, leadership, and communal trust. It forged new roles, from foremen who directed the teams to logisticians who ensured a steady supply of rollers and provisions. These engineering marvels, in turn, built the social structures that supported them. Yet, for all this logistical genius, a final, critical challenge remained at the build site itself. How do you lower a multi-ton stone into a position with such hair's-breadth accuracy that it locks perfectly with its neighbors without a single modern tool for guidance? The final stage of the journey demanded a different kind of strength, one of immense patience. A master craftsperson would stand before a freshly quarried block, a stone hammer in hand, and begin a slow, rhythmic pecking across its rough surface. Each precise tap, delivered over countless hours, would chip away tiny fragments, gradually reducing the stone's uneven contours to a flat, true plane. This was the art of stone dressing, a process where brute force gave way to meticulous control. For even harder stones like granite, they employed a brilliant form of natural sandpaper. They would rub the surface with a slurry of wet sand and a harder stone, using the abrasive quartz particles within the sand to slowly, methodically grind the stone down to a smooth finish. The goal was a perfect joint, a seam so tight between blocks that a razor blade could not slip between them. This level of precision meant the structures relied on their own perfect geometry for stability, needing little to no mortar. The result was not just structural integrity, but breathtaking visual harmony. Every surface reflected a commitment to an ideal that transcended mere function. Can you fathom the mindset required to spend days or even weeks perfecting a single block, knowing it would be one among thousands, and that its true face might be hidden forever within a wall? This was not just construction, it was an act of reverence. The cultural value was clear, perfection was a tribute, and the labor itself was a form of dedication. Each perfectly dressed stone was a silent promise of eternity. With these flawless blocks ready, the final, most delicate operation awaited, the act of locking them into their permanent, perfect positions. A single, perfectly carved stone block could now actively reach out and hold the one beside it. This was the revolutionary power of the Mortise and Tenon joint, translated from the woodworker's bench to the scale of mountains. Picture a solid knob of stone, the Tenon, projecting from the face of a massive block. Directly opposite, on the face of the neighboring block, lay its perfect negative, a hollowed-out socket known as the Mortise. When these two blocks were brought together, they clicked into place, not just resting one on top of the other, but mechanically interlocking. This was architecture that actively resisted. It was no longer a passive stack of weight, but an interconnected web of stone that could withstand the subtle shifts of the earth and the slow, inevitable settling of the ground beneath it. The same principle that held a wooden chair together was now being used to anchor entire temples for eternity. What kind of observational genius does it take to see a joinery technique in a piece of furniture and envision it carved into granite on a colossal scale? This leap of thinking reveals a society that understood materials in a deeply fluid way, seeing the underlying principles of connection as universal. The stability this provided was transformative. In regions prone to tremors, these interlocking joints allowed structures to sway as a single, flexible unit instead of crumbling apart. They turned a collection of individual stones into a cohesive, monolithic being. This was one part of a much broader system of ancient fastening methods, a hidden language of grips and clamps that silently guaranteed the survival of these monuments. The story of how these stones were locked together leads to an even deeper mystery. How did they manage to move and lift these now interconnected behemoths into the sky? Molten metal flowed into stone, binding the ancient world together. In the most critical junctions of a temple or tomb, where immense pressures would concentrate, builders carved precise channels and cavities at the joining faces of adjacent stones. They would then pour molten bronze or even iron directly into these pre-cut shapes. As the metal cooled, it contracted, pulling the stones toward each other with an unbreakable, vise-like grip. These were metal clamps and dowels, the hidden ligaments of monumental architecture. They worked silently within the structure, distributing the immense loads and stresses, preventing the subtle shifts that could, over centuries, lead to collapse. This was not just stonework anymore, it was a fusion of disciplines. The craft of the quarryman now met the art of the metalworker. The very availability of these metals began to shape architectural ambition itself. With the confidence that critical joints could be physically locked, architects could design taller columns, wider archways, and more daring structures. The stone provided the mass and permanence, while the metal provided the active, tensile strength. It was a perfect partnership of materials. How did this interdisciplinary thinking pave the way for the next logical step, not just reinforcing stone, but sculpting it into curves and perfect geometric forms? A simple bow, the kind used to start a fire, could also be harnessed to conquer granite. A worker would fix a copper tube to its string, place the tip against the stone, and begin a steady back and forth motion. The tube itself did not cut the rock. Instead, it was the magic of the abrasive slurry. Quartz sand mixed with water was fed into the contact point. Each pass of the bow dragged these incredibly hard particles under the copper, grinding away a microscopic layer of stone. This was drilling by persistent abrasion, a battle of patience over hardness. The tubular drill was especially brilliant, as it created a solid core inside the tube that could be broken free, leaving behind a perfect cylindrical hole. This opened up entirely new architectural possibilities. They could now create precise sockets for the metal dowels that locked blocks together, or drill holes for Lewis bolts, special iron devices that allowed a single stone to be lifted and set with crane-like precision. But the motivation went far beyond mere construction. This same technique allowed for the creation of hidden channels within temple walls, perhaps for ceremonial wiring or symbolic plumbing, integrating function with profound spiritual design. Why commit to such an agonizingly slow process? Each hole represented hours, sometimes days, of relentless, focused labor. The answer lies in the pursuit of permanence and perfection. A precisely drilled hole meant a perfectly seated joint, which meant a structure that would defy time itself. This meticulous drilling was also a strategic prelude, often marking the first step in the most dramatic act of stone cutting, the controlled splitting of massive blocks. The quiet patience of the drill gave way to the dramatic power of controlled fracture. Along a predetermined line on a granite surface, a quarry worker would carefully chisel a series of evenly spaced slots. Into each slot, they would place a pair of curved metal strips, the feathers, and then drive a dry wooden wedge between them. The setup looked almost delicate. Then water was poured over the wedges. Slowly, almost imperceptibly at first, the wood began to swell. Trapped within the unyielding stone, this swelling generated a colossal, relentless pressure. With a sharp, resonant crack, the granite would split, cleaving perfectly along the line of slots. This was the wedge and feather method, a brilliant act of engineering that turned the natural property of wood into a precise cutting tool. It transformed quarrying from a chaotic exercise of brute force into a predictable science. Workers could now extract blocks of specific, consistent dimensions, dramatically reducing waste and improving the safety of the entire operation. Think about the profound shift this represents. Instead of fighting the stone, they were inviting the stone to split itself, using a fundamental law of nature to do the work. This principle of harnessing natural forces, of working with the material rather than against it, became a cornerstone of architectural progress. The knowledge of this technique did not remain in one place. Evidence of the wedge and feather method appears in ancient quarries from Egypt to Greece and later across the Roman Empire. It was a technological idea that traveled, adopted and refined by different cultures who all faced the same fundamental challenge of freeing stone from the earth. This mastery of straight lines and controlled splits was revolutionary, but it presented a new creative challenge. How could these principles of force and fracture be adapted to create the graceful curves of an arch or the smooth surface of a colossal statue? The straight line had been conquered, but the curve was the next frontier. The straight line is a simple command, but the curve is a whispered secret. To move from stacking blocks to crafting an arch required a complete reimagining of geometry itself. An architect would first draw a perfect semicircle, the template for an opening that could span a space far wider than any single stone lintel. Then came the true genius. Each stone in the arch was not a rectangle, but a precisely calculated wedge, a voussoir. When these wedges were assembled over a temporary wooden frame and the central keystone was tapped into place at the apex, something magical happened. The weight of the structure above was transformed from a downward force into a lateral thrust, channeling compression through each interlocking stone and down into the supporting piers. The arch actively supported itself, each piece holding its neighbors in a perfect, balanced grip. This was not just building, it was a physical manifestation of a mathematical principle. The conceptual leap was staggering. It meant thinking not in terms of passive weight, but in terms of active force and counterforce. Why would a culture shift from the post and lintel simplicity of Egypt to the complex curves of Rome? Wider openings created vast, unobstructed interior spaces perfect for public gatherings, for bathhouses, for the flow of water through aqueducts, and later, for the soaring verticality of Gothic cathedrals that seemed to reach for the heavens. The arch was both a practical solution and a profound cultural statement, enabling new forms of communal life and spiritual expression. Yet, this structural revolution was accompanied by a parallel evolution in artistry. Once the arch proved its strength, the stone itself began to tell stories. The surfaces of these powerful forms became canvases for intricate carvings, from the crisp geometries of Roman ornament to the flowing botanical motifs that adorned medieval gateways. The stone was no longer just a structural element. It was a medium for identity, faith, and beauty, proving that true architectural mastery lies in the seamless fusion of unwavering strength and expressive detail. The chisel's final purpose was not merely to build but to speak. With the monumental walls of temples and tombs now standing true, a new class of artisans stepped forward, armed with tools refined to an exquisite point. Their task was to cover these vast stone canvases with meaning, to transform mute rock into a permanent record of history, belief, and royal power. They worked with fine copper and bronze chisels, their tips hardened for precision, and a variety of abrasive pastes made from sand and ground stone. Each tap of the mallet was a calculated risk, flaking away tiny fragments to create the crisp edges of a hieroglyphic symbol or the flowing contours of a god's profile. This was the art of relief carving, where the stone itself was persuaded to tell a story. In sunken relief, the background was carefully cut away, leaving the figures standing proud. In incised carving, the artist cut directly into the flat surface, creating elegant lines that held pigment. The entire surface of a building became a page, a sacred text written not with ink but with light and shadow. Can you see the dual purpose emerging? A pyramid was a tomb, a functional structure for a specific purpose, but its surrounding temples, covered in intricate carvings, were a library and a gallery. They were a declaration of identity meant to inspire awe and command reverence for millennia. This decorative demand, in turn, drove technical improvements. To carve a perfectly straight line for a ceremonial text, a sculptor needed an absolutely flat and smooth surface. This pushed quarry workers and stone dressers to new heights of perfection. The desire for more complex, lifelike scenes required even finer chisels and a deeper understanding of the stone's grain to prevent catastrophic cracks. The art of decoration was not an afterthought. It was the final, essential layer of the architectural process, proving that the ultimate strength of a monument lies as much in the stories it carries as in the stones that hold it up. A knotted rope became a master builder's most powerful tool. Long before the first stone was ever cut, the entire design of a temple or pyramid was laid out on the ground with astonishing precision. Using ropes tied with knots at specific intervals, they could create perfect right angles and square foundations. This practical application of geometry, often based on what we now call Pythagorean triples, was the invisible blueprint for every structure that followed. With simple tools like wooden compasses to scribe circles and set squares to check angles, they translated mathematical principles into physical reality. This was not abstract math for its own sake. It was a functional language for ensuring symmetry, alignment, and a deep sense of proportional harmony. A column's height, the spacing between pillars, the slope of a wall, all were governed by these consistent, repeatable rules. This mathematical foundation allowed for the seamless integration of complex elements, from the graceful flair of a column to the intricate patterns of an entablature. The universality of these principles is staggering. The same geometric truths that guided an Egyptian architect are still used by designers and engineers today. How were these rigorous standards communicated across generations without formal blueprints or digital files? The knowledge was likely passed down through apprenticeships, a living tradition where master builders taught their students the sacred ratios and the feel of the tools. Accurate layout was the non-negotiable first step, the grand plan that gave every stone cutter and mason the confidence that their individual piece would fit into a harmonious whole. This geometric certainty was the silent partner to every physical innovation, but it also required a new level of organization, a system to manage the thousands of precisely cut stones now being produced. That final, gleaming polish was the ultimate declaration of mastery over the stone. After all the quarrying, splitting, and carving, the surface itself could be transformed. Workers would begin with a coarse abrasive, often common quartz sand, which is harder than even granite. They would mix this with water to create a gritty slurry, then rub it over the stone's surface using a flat piece of leather or a smooth, hard rock. This was a process of persistent, methodical grinding, each pass of the tool dragging millions of microscopic quartz particles across the granite, slowly wearing down its rough peaks and valleys. As the surface became smoother, they would switch to progressively finer grades of sand, even using crushed emery for the hardest stones. The final result was a surface so smooth and reflective it could capture the light of the sun, revealing the stone's hidden depths of color and crystalline texture. This was not merely decorative, it was profoundly protective. A rough, porous stone absorbs water, which then freezes and expands, causing cracks and spalling over time. A perfectly polished surface, however, sheds water and resists the elements, locking the stone's strength in for centuries. How did this transformation influence architectural aesthetics? A polished surface interacts with light in an entirely different way. It becomes luminous, seeming to glow from within, making the structure appear less like a heavy mass of rock and more like a radiant, otherworldly object. The Great Pyramids, for instance, were once cased in brilliantly polished white Chora limestone. catching the first and last light of the day and shining like beacons across the desert. This final, lustrous finish was the visual proof of a civilization's complete control, from the raw power of the quarry to the delicate art of the polisher. It marked the end of a long, transformative journey, yet it also laid the foundation for the next great leap in human construction. A single turning wheel could now lift the weight of a mountain. The earliest cranes were likely simple winches, a wooden cylinder around which a rope was wound, turned by teams of laborers using inserted poles for leverage. This basic machine transformed the act of lifting from a collective vertical heave into a controlled rotational effort, a far more efficient application of human strength. But the true leap forward came with the addition of the pulley. A single fixed pulley only changes the direction of the force, allowing a person to pull down to lift a weight up. However, when multiple pulleys are combined into a block and tackle system, the mechanical advantage becomes profound. Each additional pulley in the system divides the required lifting force, meaning a small team could now raise a stone block that would have previously demanded 100 people pulling directly on a rope. Imagine the shift in perspective for an ancient builder. Suddenly, the vertical dimension was no longer a barrier defined by ramps and sheer manpower. It became a new frontier for construction, limited only by the strength of the ropes and the timber used in the crane itself. This mechanical advantage directly fueled architectural ambition. Why build wide and low when you could now build tall and commanding? The development of more powerful cranes, some even powered by a large, human-powered treadmill wheel, enabled the construction of multi-story temples, soaring obelisks, and the upper courses of pyramids that scraped the sky. With the power to lift stones to any required height, the final challenge was no longer about brute force, but about the delicate, final act of placement, guiding a multi-ton block into a joint so precise it would last for millennia. A stone could now reach out into empty space and remain suspended. This was the principle of corbelling, a technique of breathtaking simplicity and nerve. Builders would lay a course of stone, then lay the next course slightly inward, each block projecting a little further over the one below. Layer by layer, these stacked stones would gradually curve inward, their combined weight pressing down and locking them into place until they met at the top, forming a primitive but incredibly strong dome or arch. This entire structure was built without any temporary wooden framework or centering beneath it. It was a self-supporting puzzle from the very first stone. A closely related technique of cantilevering used the same idea to create dramatic overhangs, where a stone or beam was anchored firmly at one end, allowing the other to extend freely into the air, supporting a balcony or a bridge. The genius of both methods lay in their understanding of load distribution. Each projecting stone was a carefully calculated counterweight, channeling the forces of gravity not outward, but straight down through the wall below. This eliminated the need for massive external buttresses or complex formwork that would consume vast amounts of timber. Think of it as a staircase built in reverse, with each step supporting the one above it until the entire structure closes at the apex. What limitation did this intuition overcome? It solved the problem of spanning a space with stone when you lacked the resources or knowledge for a true curved arch. In the magnificent beehive tombs of Mycenae, this method created soaring, corbelled domes that have stood for millennia. Across the ocean, Mayan builders used precisely the same principle to construct their characteristic vaults, where steeply inclined walls of stone leaned against each other until they met. This was structural intuition at its purest, a physical understanding of balance and compression that allowed builders to make stones hold each other up in mid-air. This drive to do more with less, to achieve greater spans with minimal material, was a relentless force in ancient engineering. pushing innovation toward ever more efficient and elegant forms. Water itself became a willing partner in the quarry. Instead of fighting the seasonal floods that filled pits with mud and danger, ancient engineers began to see the potential. They carved networks of narrow channels that snaked through the quarry floor, expertly diverting groundwater away from the active work faces and into deep, purpose-built collection basins. This was more than simple drainage, it was hydraulic management. By controlling the water table, they transformed a perpetually soggy, hazardous pit into a stable, dry workspace, allowing for year-round extraction even during the rainy seasons. But their ingenuity went further. They discovered that allowing water to seep into certain layers of stone, like limestone, would actually soften the rock, making it far easier to split with wedges and chisels. What was once a destructive force was now a precise tool for facilitating the very act of extraction. Can you see the elegant logic at play? The same water that was systematically drained from one area was then strategically employed in another. They might use it to lubricate the pathways for heavy sledges, or mix it with sand to create the abrasive slurry that powered their drills and saws. This represents a profound leap in environmental thinking. Instead of confronting nature as an obstacle to be conquered, these master builders learned to read its rhythms and harness its inherent properties. How did this deep, symbiotic understanding of water enable the sheer scale of urban construction? A reliably dry, efficiently operated quarry could produce a steady, massive supply of building blocks. The grand cities, temples, and monuments that define ancient civilizations were not just feats of architectural design, but also triumphs of logistical foresight, beginning with the mastery of water in the place where the journey of every stone began. A single, repeated dimension could now build an empire. This was the quiet revolution of standardization, where the chaotic individuality of stone gave way to the power of the module. In a system like the Roman opus quadratum, blocks were not just roughly similar, they were cut to precise, interchangeable sizes, often with standard heights and varying lengths that fit together in a repeating, stable pattern. A wall was no longer a chaotic jigsaw puzzle of unique pieces, but a system of predictable components. This shift transformed the construction site from a place of constant adaptation into a streamlined assembly line. Laborers could be trained quickly to handle identical blocks, knowing exactly how each one would fit with its neighbor. The need for time-consuming on-site trimming and adjustment was dramatically reduced, accelerating the pace of building from months to weeks and from years to decades. Can you see the conceptual leap? This was the birth of industrial thinking in an ancient world, replacing the singular focus of the master craftsperson with the collective, repeatable efficiency of the system. The evidence is written in stone itself, in the endlessly repeating courses of Roman walls and the perfectly uniform blocks that paved roads stretching for thousands of miles. This reliability in production directly enabled the staggering scale of imperial infrastructure. A governor in a distant province could order a new aqueduct with the confidence that the stone shipped from a central quarry would fit perfectly with the stone cut by local laborers, because everyone was working from the same invisible template. But this new efficiency presented a final, practical challenge. A perfectly cut block was a marvel of logistics, but if it crumbled under rain and frost, the entire system failed. The pursuit of permanence now demanded a final layer of protection, a way to shield these standardized marvels from the relentless touch of time itself. A gleaming white surface was the final shield against time itself. After a block was perfectly cut, transported, and set into place, the final act of preservation began. Workers would mix slaked lime with water to create a thin, milky wash, then carefully brush or roll it onto the stone facades. This was more than just paint, it was a chemical barrier. As the lime wash dried, it underwent a process called carbonation, absorbing carbon dioxide from the air to gradually transform back into a thin, durable layer of limestone. This sacrificial coating took the brunt of the elements, slowly eroding instead of the precious structural stone beneath it. In other regions, artisans turned to the resins of trees, creating natural varnishes that repelled water and discouraged the growth of moss and lichens that could prise tiny stones apart with their roots. The foresight here is profound. These builders were not just constructing for their own time, they were actively maintaining a legacy for generations they would never meet. How did these methods adapt to local challenges? In humid, rain-drenched climates, the emphasis was on heavy, wax-based sealants that shed water like a leaf. In arid, sun-scorched deserts, lighter lime plasters reflected the harsh rays, preventing the stone from overheating and cracking. This cultural variation reveals a deep, localized understanding of environmental science. The drive to protect extended far beyond the visible surfaces, however, leading to innovations hidden deep below the ground, where the entire weight of the monument met the earth. A builder's hand rests not just on stone, but on a deep timeline of the earth itself. Before a single block was cut, these master artisans had to become practical geologists, reading the landscape to choose the perfect material for each task. They learned that a stone perfect for a hidden foundation, a dense, rough limestone that locked tightly with mortar, was entirely wrong for a delicate decorative column. For that, they needed a fine-grained sandstone or marble that could hold the sharp details of a carved goddess. This was selection by purpose, an empirical science built from generations of observation. They identified fractured layers in a quarry face, knowing those stones would split unpredictably under stress, and instead targeted the deep, unbroken strata below. They understood porosity, how a soft, absorbent stone would crumble with frost, and reserved it for protected interior spaces, while choosing hard, non-porous granite for exteriors facing the relentless elements. How was this intricate wisdom accumulated and shared? It was a living knowledge passed from experienced quarry masters to their apprentices on site. They shared rules of thumb, like examining a stone's sound when tapped or its behavior under a chisel, to instantly assess its quality. This geological intuition was their first and most powerful quality control, a primary defense against structural failure. It ensured that the brilliant engineering of corbelled arches and interlocking joints was built upon a foundation of the most resilient material the earth could provide. This careful selection process worked in perfect harmony with the next layer of their genius, the hidden techniques they used to assemble these chosen stones into a form that could actively resist the planet's slow, persistent movements. A wall was more than just stone, it was a conversation between materials. Imagine a foundation of rough, durable limestone, perfectly capable of bearing the immense weight of the structure, rising to support a superstructure of sun-dried mud brick. This was not a compromise, but a brilliant optimization. The stone provided a permanent, stable base, resistant to ground moisture and erosion, while the mud brick offered excellent insulation and was far quicker and cheaper to produce for the upper walls. This hybrid approach meant that precious, labor-intensive stone could be reserved for the most critical structural elements like cornerstones, load-bearing piers, and doorways. In other designs, massive stone piers would rise from the floor, acting as steadfast anchors from which sturdy wooden beams could then span, creating open, flexible interior spaces uncluttered by supporting walls. This synergy was the essence of architectural pragmatism. Why use a material that took a month to quarry and dress for a simple partition wall, when locally sourced brick or timber could do the job perfectly well? This thoughtful combination of materials directly shaped regional styles. In forested areas, architecture became a tapestry of stone and timber. In river valleys rich in clay, baked brick complemented stone foundations. This was a holistic philosophy, a deep understanding that no single material had to bear the entire burden. The true strength of a building came from using each element exactly where its inherent properties shone brightest, a principle that resonates in our own modern constructions, where steel, concrete, and glass each play their distinct and vital roles. The precise angle of a chisel was not just a measurement, it was a legacy passed from one hand to another. In the shadow of a half-built temple, a master mason would guide an apprentice's grip, correcting the subtle pressure on the mallet through touch and murmured instruction. There were no formal blueprints for this nuanced skill, no written manual detailing how to feel the stone's grain or listen for the telltale ring of a perfect strike. The entire continuity of stone-cutting knowledge, the accumulated genius of centuries, flowed through this intimate channel of apprenticeship. It was a living chain of learning where complex methods were not merely described but demonstrated, repeated, and refined through years of patient practice. The apprentice learned by doing, by making mistakes under a watchful eye, and by absorbing the unwritten rules that separated a stable wall from a collapsing one. This was a system that created a living repository of technical knowledge, a human library where the most valuable texts were the calloused hands of the masters. Without this direct generational transfer, the most brilliant techniques for splitting granite or setting a perfect arch could have vanished in a single generation, lost to time like so much else. This process also fundamentally shaped the social fabric. A master builder possessing such irreplaceable knowledge was not a common laborer. He was a respected artisan, a guardian of a sacred craft. His status was earned through a lifetime of dedication, and the promise of that same respect was what motivated the next generation to endure the long, arduous years of training. This oral tradition was so effective that it sustained architectural marvels for millennia, but eventually, the sheer volume of this accumulated knowledge demanded a new form of preservation. The principles that were once only felt in the hands began to be etched onto papyrus and clay, codified into the first architectural texts that would guide civilizations yet to come. The secrets of stone were no longer locked in the hands of the masters alone. A Roman scholar like Vitruvius could sit with a blank scroll and begin to translate a lifetime of tactile knowledge into the precise language of written instruction. His work, and others like it, became the first true architectural treatises, comprehensive guides that systematically detailed every stage of construction. They laid out the principles of selecting the right stone for a foundation, the precise angles for cutting a voussoir in an arch, and the ideal mixture for a durable mortar. This was a monumental shift from an oral tradition to a codified one. Advanced techniques that were once the guarded secrets of a specific guild or family of builders could now be studied by an engineer on the other side of the empire. The written word democratized architectural genius, transforming local methods into a universal toolkit for building civilization. How did this codification survive the fall of empires and the chaos of war? Unlike a master craftsman whose knowledge could be lost in a single lifetime, a scroll could be copied, transported, and hidden away in a library, preserving the core principles through centuries of political and cultural change. These texts became the stable reference point, the constant thread of technical truth that allowed new generations to recover and rebuild upon the engineering triumphs of the past. They provided the shared vocabulary and the standardized procedures that made possible the consistently ambitious projects that came to define the ancient world, from Roman aqueducts to Renaissance domes. This preservation of knowledge through writing was the ultimate insurance policy for human progress, ensuring that the art of shaping stone would never have to be fully reinvented. That new temple was more than a building. It was the community's soul given physical form. Every perfectly set stone in its walls represented a shared effort, a collective investment of labor and belief that bound people together. This was the true power of monumental architecture. It transformed abstract cultural identity into an undeniable, permanent presence on the landscape. The very ability to cut, move, and lift such massive stones was a public declaration of a society's unity and organizational genius. It demonstrated that they could coordinate thousands of workers, manage vast supply chains, and solve profound engineering challenges, all for a common purpose. The structure itself became the ultimate landmark, a source of immense pride that defined their civilization against the wilderness and against rival groups. It inspired a deep territorial loyalty, a sense that this place, anchored by this incredible building, was uniquely theirs. Sociologically, these buildings were multifaceted statements. A pyramid was not just a tomb, it was a declaration of a pharaoh's divine power and the stability of his rule. A grand temple was an expression of collective piety, showing the gods that the people were capable of great works in their honor. The architectural ambitions of a culture directly mirrored its deepest values. A society that prioritized order and the afterlife built pyramids that reached for the stars with geometric precision. A civilization focused on public life and civic virtue constructed vast amphitheaters and forums where citizens could gather. This relentless drive to build ever grander, more impressive monuments was the engine of technical progress. The desire to create a taller tower or a wider arch pushed engineers to develop stronger cranes, more stable foundations, and more sophisticated cutting techniques. The cultural need for expression, it turned out, was the very force that propelled the evolution of engineering itself. A single stone block required the coordinated effort of an entire society. The evolution of stone cutting was never just a technical story, it was a social revolution. Envision the sprawling settlement at the foot of a pyramid construction site, a temporary city housing thousands of workers. This was not a scene of chaotic toil, but a highly organized operation. Feeding this massive workforce required a steady stream of grain, fish, and beer, delivered through established trade networks that stretched across the river and deep into the countryside. Housing them demanded the construction of entire barracks and bakeries. The skilled artisan who could dress a granite block to perfection was only one part of this immense machine. His work was enabled by the administrator who kept tally of tools on a clay tablet, the surveyor who ensured the foundation was square, and the supplier who coordinated the delivery of copper chisels from distant mines. This was the birth of labor specialization on a grand scale, where a person's role could be entirely dedicated to a single, complex task within a much larger system. How did this interdependence between technology and societal structure actually work? The demand for precise stone cutting forced the development of sophisticated record-keeping to track labor, materials, and rations. It pushed mathematics forward, as officials needed to calculate volumes of stone and volumes of grain with equal accuracy. Centralized authority became essential, as only a powerful, organizing force could marshal such vast resources and coordinate the activities of so many diverse groups. The relationship was profoundly symbiotic. The ambition to build monuments drove society to become more complex, and that newfound social complexity, in turn, generated the administrative and logistical power to develop even more advanced technologies. These architectural projects were the great catalysts, forcing a leap in human organization that echoed through every aspect of life, from governance to commerce. The legacy of this interplay is all around us, in the very structure of our modern cities and corporations. a direct inheritance from the first time humans decided to move a mountain, one perfectly cut stone at a time. That first hammerstone's crack truly echoed through millennia, its simple principle evolving into the sophisticated systems that raised the pyramids, Stonehenge, and the Parthenon. This was not merely a story of tools, but a profound testament to human creativity and relentless perseverance. We witnessed the journey from brute percussion to the delicate pressure flaking that created the first sharp tools, then to the ingenious use of water and sand for drilling and polishing. We saw how a weighted string and a trough of water brought absolute precision to construction, and how the simple lever and log roller unlocked the ability to move mountains one block at a time. These were not random discoveries, but a cumulative, brilliant conversation between human ambition and the raw materials of the earth. Each technique, from the wedge and feather method that split granite with swelling wood to the interlocking joints that locked stones for eternity, reflected the cultural and intellectual heights of the civilizations that perfected them. The grand monuments they left behind are more than just piles of rock. They are libraries of forgotten knowledge written in stone. As you look at images of these ancient structures today, remember the deep ingenuity embedded in every cut and every seam. Consider how these early innovations, born from necessity and a drive for permanence, still whisper to us in our modern construction methods, in our use of cranes that echo their simple winches, and in our growing appreciation for their sustainable, locally sourced practices. Which of these techniques amazed you the most, the quiet patience of the drill or the dramatic power of controlled fracture? Share your thoughts in the comments below. If you enjoyed this deep dive into the foundations of our built world, subscribe for more journeys into the great historical mysteries. Together, let's continue to uncover the profound secrets of our shared past.